Morning to you, sir.
Okay. So we are continuing with the assembling a program using the SICK machine. So last time we were discussing what we called the machine-dependent features. And we said that these are features which determine the machine code because of the machine, that sometimes when you change the machine, the code changes. So we saw some features which can cause the code to change. So last time we were discussing the instruction formats and the addressing modes. We saw how they were generating different machine language instructions. Addressing modes, for example, for the simple SICK, there are only two, the index and the direct. But here we saw many, like a program counter, base, immediate, indirect, and so on. And you realize that whenever you use any of those addressing modes, the instruction changes. Like you saw how we are assembling using a program counter, how we are using a base, the machine language instruction is changed. And then we also saw the different formats. The simple SICK has only one format, but the SICK-XE had 4 formats. And we saw instructions of each of those formats. So the instruction is changed. The machine language which is generated changes when you also change the machine. Now, we saw in the previous section some machine-dependent features, which were the instruction formats and the addressing modes. Now there is another machine-dependent feature, which is called the program relocation. This one also affects the machine on which the program is written. Now, relocation is an English word. I think everybody knows when we talk about relocating, it means that you are maybe moving from one place to another, or you are moving from an address where you are initially known to be residing, and you are going to a new address. So I think that is what we mean by relocating. So if someone said that he's relocating, then it is obvious that maybe he's changing the address where you are used to finding him. That place will change, and then he's going to be found in another place. Now, when we talk about program relocation, we are going to be talking about what would happen if a program is given an initial address, like the programs which we have been saying. We have been saying that, okay, the program is beginning at the address 1000. Or in other cases, the program was beginning at address 00. But now what would happen if instead of that address which is given, the program is relocated to another address? What would happen if a program is relocated to another address? So that is what we are going to be discussing when we talk about program relocation. Okay. Now, usually, you should note what happens when a program is written. I think everybody knows that when you write a program, you always begin with the source code. Okay, you have the source code which you write using any editor. Okay, then the next step, after you have written your source code, the program is assembled if it is an assembler language program. If it is a machine language program, sorry, if it is a high-level program, then it is compiled. So those are the things, the steps which are conducted first. From writing the source code, if it is an assembler language program, it is going to be assembled. So what we mean by assembling is translating it to machine language. If it is a high-level program, then it is going to be compiled, okay, in order to generate the object code. The object code is the code which gets loaded in memory. So after writing the source code, you assemble, all your program is assembled by the assembler. Okay, that means machine language is generated. Then the machine language is the one which is loaded in memory, because the memory accepts only zeros and ones. So the memory will accept the object code, that code which you remember we said, which contains the source code and the instructions which will enable the program to be loaded in memory. You remember the object code, which has the header record, the text records, and then the end record. So from generating the source code, the program is assembled, and then you get the object code. Then the object code is loaded in memory. Okay. Now, when it is loaded in memory, like we know, it has got different memory locations. Okay. Now, usually when you write a program, when you are going to assemble a program to translate it to machine language, there are usually addresses which you are using, especially addresses of operands. Okay, so that means that you give addresses of operands when you are translating, when the program is being translated to machine language. That's when those addresses are generated. Remember, we discussed how a program is assembled, and we said that usually the assembler makes 2 passes. In the first pass, you generate the addresses, and then those addresses are put into a symbol table, which we call the SIM tab. Okay. Now, when that program is loaded in memory, you assume that those addresses are the ones which are going to be used. But in most cases, it is not true. Let us see an example. So in most cases, when a program is going to be loaded in memory, you remember we said that memory at any one time contains so many other programs running. So when it is going to be loaded in memory, in most cases, nobody knows where that particular program is going to be put by the operating system, because there are usually other programs which are already running in memory. So when that program which you have written is loaded into memory, you remember it is loaded after being translated, and it was translated using particular addresses. But when you load it in memory, for example, we are dealing with this simple seek instruction. If some of you can go and look at it, the simple seek instruction, which we discussed at first. we said that it is going to be loaded from an address 1000. So if it is going to be loaded from an address 1000, that's when you realize that there is this instruction which was at 10.1b, which was saying LDA 3. The starting address was 1000, but when you come to 10.1b, you find an instruction which says load the accumulator with what is at memory location 3. Okay, now at memory location 3, memory location 3 was found at the address 10.2d. Okay, so you generated a machine language instruction which was 0010.2d, because the LDA is 00, and then the operand 3 is found at address 10.2d. So you generated that machine language instruction 0010.2d. But now, instead of loading this instruction from address 00, if the operating system finds that that address which was 1000, the address which you assumed, if it is already occupied by something else, then the operating system is going to relocate the program to another suitable address. So suppose it is taken and it begins from an address 2000. But what you are loading, you are telling the assembler that load the accumulator with the 3. And then when you translate that one, you are saying that 3 is at address 10.2d. But remember, 10.2d is an address of 3, assuming that you started from 1000. But if you didn't start from 1000, the address 10.2d will not be to 10.2d, it will be something else. But you are saying that you are going to load the accumulator with what is at address 10.2d. So if you relocate the program, 10.2d will contain some very different data. It will not be the value which you want to load at 3, because the program is relocated. Okay, so that's what we mean here. We are saying that when you say load the accumulator with what is at memory location 3, and then you generate the machine language instruction, the instruction will load the register F from memory location 10.2d. But if you move the program, instead of beginning from 1000, and then the program instead is loaded from 2000 instead of 1000, the address 10.2d will not contain the expected value. It will not contain the expected value. So what we have to do is to tell the assembler that we are going to load this program in memory, but in case the address which we assumed at the beginning is not the right address where it is going to be loaded, then some changes need to be done to the program. Like that instruction is 0010.2d, which says that load the accumulator from address 10.2d. And then we realize that 10.2d will not contain the required value. Then we need to tell the assembler to adjust accordingly. Okay. Now, let me ask you a question. Suppose we are loading the accumulator with what is at address 10.2d when the program is beginning at address 1000. But now suppose the program is loaded from an address 2000 instead of 1000. where do you think will the operand 3 be found? What will be the new address of operand 3? It was at 10.2D when you started from 1000. But if you relocate this program and you take it to an address 2000, what will be the new address of the operand 3? Okay. It is going to be 202D. Very, very good. Okay. So now that is the problem, because you are now telling, if this program is loaded, you are telling it that the operand is at 10.2D because that is what is going to be read into memory. But 10.2D, like we said, is containing different data now. Okay. The actual data we need is at 22D now. The actual data we need is at 22D. So when we load the program into memory, we need to tell the assembler to change that. Instead of writing 10.2D, okay, because that is what is going to be read into memory, you tell it that in case my program is not beginning from 10.2 from 1000 and it is beginning from a different address, adjust the machine language instruction so that it does not read 10.2D, but it reads the correct address where the operand is 3 is found. So it means that some more information is going to be added to the object program to tell it to modify that machine language instruction. Okay, so this is what we mean. Okay, so what we are saying here, I hope you are hearing me. I think I had gone off. Do you hear me now?
Yes, but you are breaking. Yes, we are hearing you.
Okay. So now the objective program we are saying should contain some extra information which will enable this address portion to be changed accordingly, so that instead of reading 10.2D, it reads now 22D in case we are beginning from 2000. So an objective program which contains that extra information, an objective program which will contain that extra information, which will enable the assembler to find the right operands, is what we call the relocatable program. So a relocatable program is a program which contains the extra information required to find the actual address of the operands. Okay, so that in case of like reading 10.2D, we get instructions which will enable the correct operand 3 to be, which is now at 22D, to be the one which is going to be applied in the machine language instruction. So a relocatable program is a program which contains the extra information needed to change the address of the operands. Okay, so it is the same thing. If you look at the SeekXE program, we have got an instruction jump to subroutine RDREC. If you can see my screen there, we have an instruction which says jump to subroutine RDREC. The program was beginning at 00. Now this instruction was at 006, which was saying jump to subroutine RDREC. Now at that time, RDREC was at 1036. That was the address of RDREC. So the machine language instruction became 4B101036. You remember that was the format 4 instruction, which had the opcode, then the flags NIXDPE, and then the address of the operand. So that's why you see 1036, which was the address of RDREC. It is within the instruction. Now, if instead of beginning from 00, the program is relocated to a new address, which is 5000. It means that the instruction which was at 006 will now be found at 5006. And then the address of RDREC will now be 6036. Therefore, changes needed to be made into the machine language instruction so that the new machine language instruction is changed to 4B106036. That should be the new machine language instruction. Okay. Now, if again, you take an example that instead of loading from 00, assuming that this time it is at 7420. Okay. Hello? Someone wants to say something? Someone wants to communicate something? I don't hear you. Okay, let us continue. So this is another case. Instead of 00, suppose now the program is loaded from an address 7420. It means the instruction which was at 0006 will be found at 7426. And then the new machine language instruction will have to change to 4B18456 because now RDREC is at 8456. So in that case, you realize that the machine language instruction will need to change. Whenever you change the beginning address, even the machine language instruction will have to change if you want to find the right operand. Now, a relocatable program, like we have said, is a program which contains the extra information which will enable the machine language instruction to be changed so that it reflects the correct address of the operand. Okay. Now, like you can see, whenever you change the address, there are some things that don't change. For example, when we begin from 00, RDREC was to be found at 1036. So the difference from the beginning address to the operand 1036 to the operand RDREC is always 1036. It is the same thing here. When you begin from 5000, the address RDREC is going to be found at 6036, which is again a distance of 1036. If you relocate and you begin from 7420, RDREC will be found at 8456. Okay, again, the distance is the same. It is 1036. So this is what we are talking about in my third bullet there. When we say that no matter where the program is loaded, RD-rec will always be 1036 bytes after the starting address. It will always be 1036 bytes after the starting address. Okay. Now, how do we solve the relocation problem? Now, we need to tell the assembler, that in case a program is changed from the address which we assumed when we are generating the object code, please make sure that every operand is moved the same distance relative to the new beginning address. So that information has to be given to the assembler, that the operands should be moved the same distance relative to the beginning address. What I mean here is that if I write my program assuming that it is address 0000, and let me say I have my operand at address 50, it means that wherever I take it, the assembler has to put that operand at a distance of 50 from the new beginning address. Okay. And then after that, the address field in the instruction needs to be also changed. The address field also needs to be changed so that the new machine language instruction is reading the address with the new address. Okay. So during relocation, the assembler does those two things. It will generate the object code and it will insert the address, for example, RD-rec relative to the start of the program. What we mean is that it should always maintain the distance of the operand, okay? The number of bytes from the beginning for every operand, that should be maintained. And then the address field has to be also changed in the machine language instruction, okay? So it will also produce a command for the loader to instruct it to add the beginning address of the program to the address field in the instruction. So the instruction has to change also accordingly, okay? Now, what is done, this extra information which is needed is contained in a new record which we call a modification record. So remember, we are saying that we are going to add some information, some extra information to the object code to let it know that in case a program is relocated to a new address, kindly make sure that the operands are put into the right places. Then make sure that you change the machine language instruction so that it reads the correct address, okay? Now, those two instructions are done by what we call a modification record. You include a modification record in the object code to deliver this information, tell the assembler to modify the program in case it is relocated. So you add a modification record in case a program is going to be relocated. Okay, so the new object code will now contain 4 different records: a header record, the text records. Now we are going to add modification records, and then finally an end record. Modification records, those are going to be added in case a program is going to be relocated from the address used when you were assembling it. So a modification record begins with the character M. It begins with the character M, then followed by the starting location of the address field, which is going to be modified. We are going to see an example. Then that is followed by the length of the address field, which is going to be modified, but in half bytes. The length will be given in half bytes, okay? So let us look at this instruction here. Let us take an example of this instruction. Jump to subroutine RDREC. Okay. Now the instruction was here at 006, or if we can go back to the program. Okay. Do you see my program? Do you see the
Yes.
Okay. Now we have this instruction which is at address 0006. It is saying jump to subroutine RDREC. Okay. And like I was mentioning, RDREC is at address 1036. So that's why you see that this is a format 4 instruction. You remember it has got the opcode, then the flags NIXBPE, and then finally the address of the operand, which you see here, 1036. Finally, that address has to be there. Now, if you are going to write a modification record for this instruction, because it is going to change, if you don't begin from 00, the address of RDREC will not be 1036. It will change like the examples we have been looking at. So if you are at 0006 and you are going to write a modification record for this instruction, okay, according to the format of the modification record, you begin with, okay, according to the format of the modification record, you begin with the character M, okay, then followed by the address field, which is going to be modified. Followed by the address field, which is going to be modified. Yeah, someone is saying I'm breaking. I don't know what I should be doing. If I am breaking.
You okay now?
I'm now fine.
Yes.
Okay, thank God. Okay, so I was saying, we are looking at this instruction here, which is jump to subroutine RDREC, and its address is 1036. 1036 is the address of RDREC, so it is within the instruction. Now, we are saying that if it is at the address 0006, now address 0006 is the beginning address of that instruction. Okay, you remember we said that if it is a format 4 instruction, it is going to occupy 4 bytes, because the format 4 is 4 bytes. So that is why you see that it is from 0006 up to 000A. Is that right? Now, if it is 4 bytes, okay, and you are beginning from 0006, okay, then it is going to continue 007, 0008, 0009, And then the new instruction will begin at 000A. Now the first byte 006, okay? This first byte contains the opcode, because you remember the format, the opcode is taking like 6 bits. So most of the 4 bytes, the first byte is occupied by the opcode. It is 6 bits. So which is maybe something like approximately 8 bits. So most of the first byte is consumed by the opcode. Now from there, from the opcode, this is we begin the address field which is going to be modified. So we can say that changes will begin from address 0007, because from address 006, we have the opcode itself, which doesn't change. Okay, that one will remain constant. But from 007, that is where the changes are going to begin. So if we write a modification record, we begin with the character M, followed by the address which is going to be modified. So here, if we are at 0006, then the modification will be from 0007, okay? And then we have the what? According to the syntax of the machine, of the modification record, okay? Then we have the length of the address field to be modified in half bytes. Now for format 4, what is the length? What is the length of the address? Remember, we have got opcode, NIXBPE, and then the address. The address is how many bits? Hello? Hello? So this one is saying I am still breaking. So I don't know what I should do to avoid the breaking. Yeah, am I breaking again?
You are not. No, you are not breaking.
No, you're not.
Okay. So I was saying, I was just asking that you remember we have got the format for instruction. This one, the instruction we are looking at is a format for instruction, which is 4 bytes. That's why you see that if it starts from 0006, it will occupy 4 bytes, and then the new instruction, the next instruction, will begin from 000A. Now, I'm saying that according to the format of the modification record, you begin with the M, then that is followed by the beginning address, which I'm saying is going to be 007, not 6, because 6, that one is occupied by the opcode. So the address which is going to be changed is beginning from 7. And then finally, we are talking about the length of the address field in half bytes. So I was asking how many bits is the address field? How many bits is the address field? Format for instruction, we have opcode, then NIXBPE, and then an address. An address is 20 bits, very good. Now, if it is 20 bits, but this format is telling us that we should give the address in half bytes. Okay, that we should give the address in half bytes. The length of the address field to be modified in half bytes. So a half byte is how many bits? A half byte is how many bits?
4.
It is 4 bits, very good. So it means how many half bytes do we have in 20 bits? How many half bytes do we have in 20 bits? Okay, we have 5, very good. So that is why you see how this modification record is written. You begin with the M, okay, followed by the beginning address. The beginning address, they are telling us that it should be from 2 to 7, which means that it is occupying. How many characters are those ones? How many digits do we need? From 2 to 7. From 2 to 7, how many bits do we have there? So how is it 5 or 6? I think they should be 6 when you include even the 2, because the 2 is included. So from 2 to 7, we have 6, okay? Then we have the length of the address field in half bytes. Those are only 2 digits. From 8 to 9, those are only 2 digits. So that is why you see that the modification record for the instruction, which is at 0006, will be M, then 000007, and then 05. M, that is the first, then 00007, that is the beginning address of the field which is going to be modified, and the 05 is the length of the address in half bytes. Okay, is it clear? So that is what we are explaining in the second bullet, that the beginning address of the program is to be added to a field that begins at address 00007, and it is 5 half bytes in length. Okay? Is it okay? Sorry, I am asking, do we continue? Hello?
That address 00007 is a little bit confusing.
Okay, it seems that some people have problems. Let me repeat. What we are changing, remember we said, if I can have your attention, modification is doing 2 things. The first thing is to tell the assembler that in case a program is going to be relocated to a new address, which is different from the address we assumed when we are generating the object code, make sure that the operands are placed in the at the same distance as relative to the beginning of the program, so that an operand let me say, which was 10 bytes from the beginning address, make sure that wherever you take it, it maintains that distance, 10 bytes from the beginning. Then the second instruction, or the second task which needs to be carried out, is to change the machine language instruction which was generated at the time of assembling, okay? So that now, when you relocate the program, that address field is changed so that it reads the new address where the operand is now located, okay? So we said that those two instructions are accomplished by writing just only one modification record. So we said the modification record begins with the M, okay, followed by the beginning address of the field to be modified. Now, in this particular example which we are looking at, the instruction is beginning from address 0006, and it is occupying 4 bytes because it is a format 4 instruction. Now, if it is occupying 4 bytes, because it is a format 4 instruction, we realize that the first byte is mainly occupied by the opcode. Okay, so from the if we be beginning from 006, so it means that what is going to change will be from 007, because 006 is occupied by the what? By the opcode, and the opcode does not change wherever you take the instruction. It is the address which changes. So we modify from 0007. Not 006, but 007, because at 0006, there is the opcode, okay? So that's why we say 0007, because at 006, we have the opcode. Now, when it comes to the address field, the address field is 20 bytes, 20 bits. And they want us to express that in half bytes. So we said that within 20 bits, you have 5 half bytes. So that's why we have M 00007, that is the next field, and then 05. That means indicates the 20 bits for the address, okay? Now, someone was asking that if it is...
You are breaking.
I don't know what I should do now. If I am breaking.